is out of service. It's just several minutes ago. So yeah, I'm sorry. Yeah, that's okay. Can you say right now? Can you say my exam sheet? Low. Okay, I will share. Yeah, don't worry about it. Okay, I will share this exam sheet. Oh, what happens? Cannot share. Okay. Then let's take a look at it again. Okay, let's see. Yeah, and let's just share this with you guys. Okay. I guess I did close this WebEx meeting. Then I will restart it again. Yeah, right now.
Professor,
I cannot. Okay.
It shows that Michael Shimanga is the presenter, so I think you have to be the presenter to present it, to share the
Oh,
slide.
really? Okay.
Yes.
Oh, okay. Oh, thank you. Yeah. Okay. Okay. Then I can take a look at it. Oh, yeah. Thank you. Yeah, I got it. Okay. Then I will share this file with you. Okay. Right now, can you see my exam sheet?
Yes, Professor, we can see it.
Okay, that's good. Thank you. Yeah. Okay. Yeah. Third question, the part B, we said we did use the bootstrap to estimate this standard error. Yeah, so you just search for the bootstrap. We just do the resampling to generate the bootstrap data. Yeah, from the original data, you generate your bootstrap data. If you repeat this process, for example, like the 1,000 times, you can get the 1,000 estimate of this regression coefficient. So that just means you got the 1,000 this regression coefficient estimate. Then pretty sure based on this 1,000 regression coefficient estimate, you can calculate this standard deviation. This is the estimate standard deviation. So this is the basic idea we do there. Yeah. Okay. The fourth one, this I guess the problem 4 should be pretty simple. We say we want to build a regression model that have the many observations and many predict. We say from the computational point of view, which of these two methods to this model building algorithm are preferable? Definitely is this forward selection method, forward stepwise selection. Yeah, this is definitely that's clear there. This is for the computational way. Pretty sure you can say, for the best subset selection method, let's use the whiteboard. I will share the whiteboard with you guys. Just wait 1 minute. Okay. Oh, that's a little bit slowly. Okay.
Professor, can best subset and forward stepwise selection give the same result after a given k number of predictions, like k number of subsets?
Not really. I will explain for you.
Okay.
You can see here. Okay. I will share this whiteboard with you guys. Today it's a little bit slow for this internet. Okay, I will share this whiteboard with you guys. Yeah. Okay. Right now, can you see my whiteboard?
Yes, Professor.
Okay. Yeah, we can say there's two methods there. So one is the forward stepwise selection, forward selection there. Another one, best subset selection. You just consider the candidate. How many models we consider? You can say for the best subselection models, the possible model we have considered is 2 to the power p. This is a possible models there. The p is the number of the predictors. But you can say for the stepwise selection, you only consider around the number is about the p squares. So you can say that's so small there. You can quickly think about it. If p is the, you just say it's 100. You can quickly discuss. For example, if p is around the 100, then p square is around the 1000. That's true, 10,000. But you can take a look at for here. The best subset selection, you did consider 2 to the power 100. That's a very large number. So they are so much different. So you can say here you did around this so large number of this model fitting. It's this way there. So you can say from the computational way, definitely you did use the forward stepwise selection. This is okay? Can you got it? Yeah, okay. This is this one there. This is for the computer. Second is the true or false and explain. Best subset selection will result in a small prediction error than forward stepwise selection, because every model that is considered in forward stepwise selection is also considered in the best model. This part, definitely this explanation, the reason is true, but the result is not true, because this is the prediction error is just the test error. So you can say if we consider the training errors, definitely best subset selection will result in a smaller training error than this forward stepwise selection. But that does not mean it will result in a smaller test error. You know that. That's the thing there. So sometimes this, you do this too much this kind of searching in this kind of large this kind of possible model space. Definitely this might be you found the best model overfitting the data well. You have a pretty overfitting there. So finally, when you use this model to do the prediction, it will not the good result. This is okay? Yeah, so that's just means best subset selection will not result in a small prediction error, even though certainly they consider much more models than the forward stepwise selection. Can you got it? Yeah, okay. Then we can take a look at the question 5. This question 5, this we just covered in the chapter 6. We say write down the expression that one needs to minimize in order to get the parameter estimate of the lasso. That's pretty clear there. For lasso, this is just the penalizer regression. What we did, you can say, what's the goal there? We want to minimize. This kind of definitely one is a residual sum square plus this kind of penalty term. The absolute, this kind of the coefficient, the sum of the absolute coefficient. This is the lasso. Similarly, for the rigid regression, this is L1 penalty. We said there. You say for the rigid regression, just the L2 penalty. The same thing there. The only thing is this one there. the sum of squared coefficients. So this is L2 penalty, the only difference. So this is for the part A and part B. We say compare the models. These two methods produce. Which one is typical, is more interpretable, and why? Definitely it's the Lasso. Because Lasso accepts to do the shrinkage of the coefficient estimate. It can also do the model selection. So for when you do the model selection, that just means you can produce a smaller model fitting. That's true. If we produce a smaller model, only include a smaller number of the predictor, definitely this model is more interpretable. This one. The reason is it can do this kind of variable selection, but we know the rigid regression cannot do the variable selection. So if you include 100 predictor in the model, finally it still have this 100 predictor there. If you have include 1,000 predictors, final model still have this 1,000 predictor there. So for the rigid regression, this is less interpretable. This is part C. Is the prediction error of the Lasso is always smaller than the part D. The prediction error of the Lasso is always smaller than the rigid regression. It's definitely that's low. Yeah, some case it has a smaller prediction error case. Some case it's a lot. Yeah, if low, what is the typical situation where whether this rigid regression will do the better? Definitely low for this kind of the general case. If we have a number of this kind of predictors, that is related, which are related to the response. There is a pretty large number of the predictors related to the response. Then rigid regression will work well. If we only have a very small, very few predictors are related to the response, then Lasso will work better. I guess in the class we showed this graphs there. This is okay. Yeah, this is for the question 5. Yeah. Okay, and then we can take a look at the last question. This is, yeah, here, for this code, definitely you guys have used a lot. We say the question problem 6. Suppose we are trying to model a classification problem with two labels, the sick and the healthy. From the purpose of the test, we consider positive result to be testing sick and the negative to be the testing the healthy. Yeah. So after fitting the model with the LDA in R, we compare the predicted values from the actual value. So you can say this is your actual value. This is your predicted value. That's true. Yeah. So we say what is the misclassification rate for the model power? That's pretty simple there. You can say here. You can say how many misclassification we have. Yeah, you can say here we have the 32. These healthy people, they are misclassified as the sick. That's true. Another one we have the 25. The sick people, they are misclassified as the healthy. So finally, the total number of the misclassification is the 32 plus 25. So that will be 57. Certainly, if you divide by the total number of the people, you got your misclassification rate. So that will be, then you got it. So that will be 32 plus 25 divided by the total the sum of these 4 cells counts. That's a misclassification rate. That is okay. Can you got it? Okay. This is one thing there. Okay, then we can take a look at the second. How can we decrease the rate of the false positive to the false negative in LDA? So you can say this is what it look like for LDA. How do you do that? So let's say roughly you use a graph, you quickly got it. Like say we have this kind of the cross this things. We say this is the healthy people. So we use this kind of circle to denote this sick people. Yeah, certainly might be here you got something there. This is so you say you got this one. This is your this kind of decision boundary to separate this observations as a two part. Certainly, if it's certainly left side, this part, this is we predict to be the healthy. This part, the right part, we predict to be the sick. That's true. So you can say, so you quickly say, oh, sorry. So you can say, if you want to reduce the rate of the false positive, the reduce of the false positive. So what's the false positive? So that just means this guy is healthy, but you misclassified as the sick. We say this is the false positive. That's true. You make sure you are clear there. This is false positive. What does that mean? Yeah. So that just means some people are this is the healthy, but you misclassified as the sick. Then what is the false negative? So that's a false negative. Definitely, that just means this guy is sick. Is sick. I misclassified as the healthy. So that will be the false negative. So here you want to say, okay, let's reduce the rate of the false positive. Reduce the false positive. Then what that means there? So that just means we will predict fewer observations to be the positive. That's true. So that just means this hyperplane will move to this part. That's true. Then certainly if you move to this part, then certainly, this part to the right. If you move your hyperplane to the right, then certainly you will predict fewer observation to be the positive. That's true. If you want to increase this kind of the false positive rate, you will move your hyperplane, this kind of the hyperplane to the left side. Can you got it? Yeah. Oh, just wait a minute. Okay. So you can say the whole idea is to say, okay, I will change this kind of thresholding. I will change my thresholding. Yeah, I will change the thresholding to the left hand side. Someone have some question? We have to make the model more flexible. This is not relevant to the model. It's relevant to your boundary, to your thresholding. Yeah, let's just give you guys an example. You are more clear. You can quickly take a look at this one. Do you remember for the logical regression? This might be more clear. Logical regression. Yeah, you can say for the logical regression, degree of the polynomial not related to this one. I will explain to you guys. So you can say here, for the logical regression, what we did it, we logarithm this kind of the probability of the y equal to 1 given your predictor, let's say given your predictor that 1, then certainly it's this one, y equal to the 0. Certainly you model this one. Let's say this is the beta 0 plus beta 1x. That's true. Then certainly you say after we got the estimate of this beta 0 and beta 1, you got your fitted model. Then certainly you say, okay, this is your fitted model, given a test sample. How do you make the predictor? For example, given x equal to the x0, how do we make the predictor? So very quickly you say for this one, how do you do? Okay, then we say, okay, let's just calculate this, we will count it. For this, for the left hand side, it's the positive or it's negative. If this guy is a positive, then we say this sample will from class 1, otherwise we say this from class 0. That's true? So what does that mean there? That just means if the probability y equal to 1 given this kind of x equal to x0, if greater than 0.5, we say this guy is from the class 1. Otherwise, let's say class 0. That's true. So you can say here, the threshold is 0.5. That's true. So certainly you say, okay, let's change it. Not 0.5. How about 0.6? If it's 0.6, then certainly that's hard. You predict the test sample is from the positive class. But if it's the threshold, you change you reduce from 0.5 to 0.4, that will be more easier predict the test sample is from this sick class. So if we increase this threshold from 0.5 to 0.6, then definitely we will predict more fewer observation from this positive class. Definitely this false positive rate will be reduced. Is okay? This is for the logical regression. Similarly for the this LDA is the same this kind of understanding. Can you got it? Okay. Yeah. Okay. That's good. Yeah. So that's this one. So you can say, pretty sure you can. This is how do we do? How do we reduce the rate of the false positive? The main thing you just increase the value of the threshold. Yeah. Second one, why we may want to do this way? This you can also easy to understand why. You can say, let's just say that if we just these two classes, why we want to do that? If this one, just this is two classes. If say class 1 is the people got the cold lighting. Class 2 just this kind of healthy people. You can say what's the false positive? So for the false positive, that just means one guy got the cold lighting, but we mispredict as the healthy people. That's true. So this cold lighting, they got this one, but we say they are the healthy. Second one, what's the false negative? For the false negative, that just means this guy is healthy. but we misclassified as the COVID-19. So you quickly say, you can say for these two, this kind of errors, false positive and false negative, which one is more serious? Definitely is this one. Because if some guy got the COVID-19, you said, oh, he's healthy. Then he may just got around. Yeah, he just attended this kind of party or whatever, this kind of gathering there. Then he will affect a lot of people. But if some guy got the healthy, but we misclassified as this kind of the COVID-19, this definitely it has a little bit effect about on this person's individual life, but not so big deal. So that just means this cost, they are so different. Let's say this cost C1, this cost is C2. For this case, might be the cost C1 is much larger than cost C2. Yeah. So that just means false positive is much more serious than the false negative. So under that case, definitely we want to reduce this kind of the false positive rate. At the same time, definitely you increase this false negative rate. That's not a big deal because their costs are different. Yeah, this one. So this is why we do this one. Yeah. Okay, then. And here we just assume the LDA is a good method. So if this guy is a good model for the data, so this LDA will be pretty close to the optimal algorithm, like the Bayes algorithm. Then how is likely affect this misclassification rate? Certainly, originally, for this LDA, its misclassification rate almost the optimal. So it almost have the smallest misclassification rate. But right now, you change the threshold. Definitely, this misclassification rate will be increased. Yeah. This is okay? Yeah. This is certainly, this is a little bit relevant to the imbalanced classification problem. Certainly in class, I mentioned a little bit. But for the last question, certainly I hope you guys can do a little bit deeper thinking. If you didn't get it, was okay. Yeah. Any question? No? Okay. Okay, that's good. Don't worry about it. I told you I haven't finished the whole gradings. Yeah, after finish grading, I will take a look at whether we did make a little bit this kind of adjustment on the gradings or not. If most students have done well, definitely I don't want to do any adjustment. If many students haven't done so well, certainly I will make this kind of some adjustment of the gradings. Don't worry about it. Yeah. Any other question about this midterm exam? No? Do you feel the question is okay? Yeah, do you feel it's or too simple or too challenging? Whatever. Yeah. If you guys feel this kind of exam question, you just feel it's okay. I guess in the future, for the final exam, maybe we will prepare the similar questions. Okay. Some students mentioned they said this kind of questions are a little bit difficult to him. I guess for the Daniel, he mentioned this question is difficult. Yeah. How about the other students? Do you feel it's fine, or we just make the questions become a little bit simpler? Yeah. If you have any this kind of comment or suggestions, you can let me know. Otherwise, I just feel, this is For the multiple choice, it's better. Usually we will not use it. For the graduate course, usually we will not have this kind of the multiple choice question for you guys. Yeah. Okay, some more direct. Okay, I will think about it. Yeah, ask you guys more direct question. But definitely for the multiple choice questions, usually we will not do it. This is most usually for the multiple choice questions, just for the undergraduate student. For the graduate student, usually we just have this kind of a little bit of conceptual question or a little bit of computational question. Yeah. Okay. Okay. Another one they say, okay, just feel some questions. Okay. Okay. It's yeah, I guess might be only the last question a little bit hard. Yeah, a little bit hard, but I guess it's helpful for you guys. You can do a little bit of thinking. Yeah, a little bit actual thinking there. If it's all question is too straightforward, you guys might feel pretty boring. But don't worry about it. I told you, I said after I finish the whole grading, I will base on the you guys' performance, I will make a little bit this kind of adjustment under this kind of gradings. Don't worry about it. Okay. Some people ask just like for the last question, what are the models we can choose to fit the data better? That's a good question. For this kind of the imbalanced classification problem, definitely some of this kind of the tactics has been developed. One way is to handle the data. To handle the data, they change the data from the imbalanced to become the balanced case. Then using the standard method. This is one thing they do. Another one, they focus on the algorithm. Focus on the algorithm. Then they just, like I mentioned, they change the threshold. So there's two different ways there. Yeah. Okay. Yeah, that's a good there. Yeah. There's two ways. For example, one, there is a pretty popular method like the smooth. Actually, they just do this kind of they change the original data they make it from balanced. This unbalanced become balanced. But the lot of thing it's a limitation. Is this kind of method is hard to explain. Why do this kind of the changing? This kind of the will works well. Yeah, so that's it's hard to explain there. The only thing people have done some this kind of the computation or simulation, they show okay after make this kind of modification of the original data, it can work well. Yeah. Okay, certainly if you are interested, you can directly use Google to search it. Using Google, yeah, for example, to just input this imbalanced classification. I guess there is a lot of these tutorials available. You can quickly take a look at. They provide a very simple explanation of some basic algorithm and also provide data there. You can take a look at. Okay. Thanks for your guys' this kind of input. Pretty sure in the final exam, I will make a little bit of change. Make sure you guys feel more comfortable. Yeah, don't worry about it. Even for the midterm, I told you, based on most student performance, if needed, I will make a adjustment of the grading. Yeah, don't worry about it. Okay. Do we have any other questions regarding this midterm exam? No? Okay, if no question, then we will, let's first take a break. take the 8 minutes break. Then we will move to the chapter 7 about this nonlinear models. Yeah. Okay. You can take a break, 8 minutes break. We will get back at the 7.